Project 3, where we will be talking about exponents and logarithms. So when we start talking about exponents, we need to talk about both exponential growth and exponential decay. Here's a picture of the graph of an exponential growth. You'll notice that it starts relatively flat and then spikes up. The equation for exponential growth is y equals a times b to the x, where b is greater than 1. This is actually pretty important because we'll see that the exponential decay model is the same with a different requirement regarding b. Remember that the domain of a function talks about what inputs can go into that function. While this graph only shows the function starting at 0, it does continue on forever in this direction. It also continues on forever to the right. Even though it looks like it's spiking straight up, it still is moving to the right. So the domain is negative infinity to positive infinity, meaning that you can plug any x into this function, which makes sense because if you think about it, any number could be an exponent. If it's 0, the result will be 1. If it's positive, the number will just keep getting bigger, and if it's negative, it'll start turning the base into a fraction. Remember that the range talks about what outputs are possible. This part of the graph is showing that the graph is going up forever, which means there is no upper limit on how high this graph could get. However, while this is trending downward, it will never actually get to 0. So the range for this function is 0 to infinity, which again should make sense. Even if x starts getting very, very small and negative, so something like negative 1,000, that would just turn the base into 1 over b to the 1,000th, which for any number would stay positive. The domain and range do depend on a being positive. This graph would flip upside down, and the range would then change if a were negative. Here's an image of what exponential decay looks like. Notice that the exponential decay formula is the same as exponential growth, but now b must be between 0 and 1. While we are spiking in this direction to the left, this graph actually could plug in any x that we want, as it goes forever left and forever right. So our domain is once again negative infinity to positive infinity. While this is getting lower here as you move to the right, it will never reach 0 again. And this upward movement will never stop. So our range is again 0 to infinity. Once again, this requirement is dependent on a being positive. The graph would flip upside down, reversing our range if a were negative. So as we look at growth and decay side by side, we see that as long as a is positive, we will have the same domain and range regardless of whether or not it's growth or decay. Notice that the model looks the same for both. It's all about whether or not our base is greater than 1, leading to growth, or between 0 and 1, leading to decay. If b were to be less than 0, this would be neither growth nor decay. So let's take a look at some examples. Are these growth or are these decay? The big thing we're looking for is an x in the exponent, which we have, and then what is the base? Well, our base here is 0.5, which is between 0 and 1, which means this is decay. In the next problem, x is upstairs, which is what we're looking for. That means this is exponential. And our base, what's attached to that exponent, is greater than 1, meaning this is growth. Finally, in this last example, we do not have an exponent. The x is downstairs. That means that this is neither growth nor decay. This would actually be linear. In order to solve an exponential equation, you'll need to use logarithms, which we call logs. Imagine we have this problem that says 3 to the x equals 72. A lot of people will want to divide by 3 here, but that does not work. That wouldn't isolate x because x would still be upstairs. Instead, we use logarithms. If I log base 3 both sides, logging an exponent with the same matching base cancels out the base of the exponent and isolates x. So now we have x equals log base 3 of 72. We're going to use something called the change of base formula. Change of base formula says that if I take the natural log of the number that's being logged divided by the natural log of the base, I'll get an equivalent expression. The reason we would want to do this is because ln of 72 over ln of 3 is much easier to type into a calculator. When we do type it into the calculator, we get an answer of 3.89, which would be our solution. In some cases, we will be given an exponential model to represent a real-world situation. In this example, we're told a radioactive spill exposes local residents to 450 MSV of radiation. So T represents the number of days. E is a number called the natural number. Kind of like how pi is 3.14, e has a designated value. And given the context of this problem, a must represent how much radioactive waste remains after t days. Now in the question they ask us how much of the radioactive waste remains after 8 days. This is telling us that t equals 8. So we're going to take this model and we're going to plug in 8 for t. From here, we should be able to type this into a calculator. On the Desmos graphing calculator, you can find e under the function tab. I'll click e to the x and type in negative 0.25 times 8. We get an answer of 60.9. So 60.9 MSV is how much waste remains after 8 days. Now, using the same context, let's do a problem where they make us go the other way. If 300 MSV is the safe amount of radiation, how long until this area is safe? Well, 350 is an amount of radiation, so we're going to plug that in for A. And how long means we're looking for a t, so we're trying to solve for t. Before I can solve for t, I need to get this power alone, which means I need to divide both sides by 450. This gives us 0.78 equals e to the negative 0.25 t. Like we did in the earlier problem, we would want to log both sides with the base of the power. But logging with a base e is the same thing as natural logging. So really we're going to natural log both sides. This gets rid of the e and leaves us with ln 0.78 on the other side. Unlike the earlier problem where we needed to do the change of base formula, ln of 0.78 is already something that's easy to type in the calculator. To keep things a little more exact, I'm going to wait to the end of the problem to type that in. Next, I'm going to divide by negative 0.25 to solve for t. And now we have t equals ln of 0.78 divided by negative 0.25. This is something I can type back into the calculator. And I get an answer of 0.99. That means it'll take about 1 day for the radiation amount to get back down to a safe level. The compound interest formula provided here is another important exponential equation that's used in the real world. In this formula, you have P, which is principal, N, which is a number of compounds, R, which is an interest rate, and T, which is the period of time for which the interest will be growing. If we invest in an account that pays 10% quarterly, our rate is 0.10, the number of compounds per time period would be 4, and we don't know principal and time, so those will be left as P and T. So let's fill out the model. So I plug in all of those important pieces of information, and here's our model for that interest rate and that number of compounds. Here's a little guide to some of the popular terms that could be used for the number of compounds and what number of compounds goes with it. Let's do one last problem where they ask us how long it will take to triple your money. Given that they're saying 10% quarterly, we can use the model from the last problem. There are currently 3 unknown variables: y, which is how much money you'll have at the end, p, which is how much money you have at the beginning, and t, which is how long it takes to get there. When they say how long, they're saying we still don't know t. But by tripling our money, we could use an example to be able to solve for t. I'm going to replace p with 1, and if you triple 1, you should get back 3. So I'll plug in 3 for y. Now I have an equation set up that I could use to solve for t. By simplifying inside the parentheses and getting rid of multiplying by 1, I get this simpler equation. Now we can log base 1.025 both sides to get us out of exponent form, and we get log 1.025 of 3 equals 4t. Change of base formula brings us to ln of 3 equals ln of 1.025, which our calculator tells us is 44.49, and then we'll divide both sides by 4, which our calculator tells us is 11.12, which means it'll take 11.12 years in order to triple your money. There was a lot crammed into this lesson, but here's a few key takeaways. A function is only exponential if there's a variable up in the exponent. If you need to solve for a variable in an exponent, log both sides with the same base as the exponent. And finally, make sure you know how to use the change of base formula, as that will be important in our projects. If you came away with anything else, write it down now. Otherwise, we'll see you next time.